So now let's have a look at the tasks. So the first task is to implement the body of the method find dead signatures in the class alloy checker. So let's first find that class and find that method. I already created them there. So that's in the class alloy checker, we should implement the find dead signatures. Right now, it doesn't do anything. The parameters that it gets is a file name. So in this example using the compiler, we saw how we can read stuff from files. That's what we'll probably have to do. Options, that's something we don't need to care about. This sets something like the SAT solver to use because Alloy could use multiple SAT solvers. Here, I'm actually setting this in the test cases. So if we want to look at the test cases for find dead signatures, then we see here that I'm modifying these options to set the SAT solver SAT for J, which is a Java implementation of a SAT solver. So this should work on all machines. Good. So then there is this Alloy reporter. Here in the test cases, I'm just setting the no operation reporter that basically ignores everything. It doesn't really do any reporting, which is not important for us right now. So you can ignore this reporter and the options. The only really important thing for you is the file name. You might need these, as you saw in the examples. Examples using the compiler. At some point, you will need to use some reporter when you do, for example, execute command, and you might need to use some options here in the same. So then you should, of course, use the ones that are passed to the method. So don't use any other options or SAT solvers, just use the ones provided to you in this method here. And then there is some further information on this task. So it points to some of the concrete examples where you might find help in necessary pieces that you need to know if you programmatically want to operate on Alloy modules. So yeah, how are you going to access the commands? Because here we're only going to focus on the very first command. So use the first command in the Alloy file only. Alloy files might have multiple commands. We don't care for this analysis of dead signatures, which of course could depend on the commands. We're just using the very first one. And you can see how to access the commands in this provided example. Then you don't want to really find dead signatures by iterating over solutions, I would guess. So then you probably need to kind of modify the predicate in the command that you're running. So here in this example of the list, which is one example that is used in the test cases, we're running the predicate cyclic, right? You probably want to update that programmatically in some way so that you can easily check whether a signature is dead or not. And yeah, you will see some way of modifying or creating formulas from signatures in line 90 of this example using the API. So you can have a look there, try to understand that code that is provided in example using the compiler and example using the API. And then for a given command that you want to analyze, you need to modify the formula that you're checking, and you can do that simply by calling command change with the new formula that you want to set. Okay, so I can maybe give a very, very brief demo of how we would do this, but now I'm going to do it manually here in typing this kind of stuff. So I don't only want to run a cyclic, I want to check whether signatures are dead. So how do I find out whether they're dead? If I can not find an instance where this signature is actually instantiated. So let me try to say and some list. Now, this and some list is something I added to the predicate. Now, if I run this, I find an instance, which is very good because then I know that list is not dead. If I say and some node, I run this, I find an instance. I know that node is not that, so I don't have to go over all the signatures. I can basically just modify the formula and then figure out whether a signature is dead or not. But now you will do this programmatically. So you're not going to do this manually. You're going to do that programmatically by trying to understand how Alloy uses these kind of APIs internally. Yeah, and then the only thing that is left to do is basically to kind of iterate over the signatures and then store the signature names. So if you have a signature, then to get the name, that's simply the signature.label. Not sure if we have this somewhere here. Okay, not in this example. Not in this example, but that's basically, here we have some signatures like A and B. So if we wanted the name of signature A, we would simply say a dot label. And this would be the name of that signature. So that's the stuff we would add to our list in the end. Okay, and then this is tested using these test cases. So they basically take the pass the list alloy module to your method, and then it checks that there should be no dead signatures. I mean, we just analyzed this manually and we found out that list and node, they're both not dead. So we would basically give an empty list of signatures because these are the only signatures here defined by the user. Yeah, and then it analyzes a few other ones. You can see all the other ones that it analyzes in this source main resources folder. So that is task 1. Then task 2, very, very similar. Instead of finding the dead signatures, we need to find the core signatures. So signatures that have to be in all instances. Now, yeah, if this was the, so you probably, again, want to kind of modify this code and see what's going on here. Just by looking at it, we know that list is core because it always says one list. And node, we don't know, could be core, could not be core. So we could check, is there an instance where the command is satisfied, but there is no node. So, and no node. Now, there is an instance. This means that node is not a core signature because there is an instance without nodes. Good. So that's kind of the idea behind core signatures. Very similar. You have a very, very similar structure, but you will change the command formula slightly in a different way and interpret the result in a slightly different way. And then task 3 is a bit more tricky. Here the idea is to find a minimum scope. The scope is always the kind of the number that we associate with the signatures, the size that a signature can be at most. So here we say 4, 3, which gives an upper bound for node. The number of nodes is less or equal to 3. The number of lists is actually less or equal to 1 because of this one signature. Now, the question is, what are, let's say, the minimal scopes that we could add or that we could set for a command and a signature to make sure that the command is still satisfiable. So that's basically the idea of this analysis. For every single signature, we would want to find the minimal scope with which the command is still satisfiable. So in this case, now this looks slightly different. So if we manually wanted to check it, we would have to check, well, what's the maximum scope that node could have? if we want to check it for node, then, well, the maximum is this 3. So we could check, does it work for 3 node? And we see, yes, with 3 nodes, it might work. Does it work if we restrict node to be at most 2? We see here now the node scope changed. Still an instance, yes, if we restrict node to be at most 1. Still an instance, if we restrict node to be of size 0. There is still an instance, so everything is fine. The minimum scope for node would thus be 0. Now we could try the same for lists, right? So let's say here default scope is 3, so let's try 3 list. Now we see there's a syntax error. Syntax error in Alloy, if you run it using the API, would mean you get an exception. So you need to catch that exception if you come across it and kind of ignore this case. So then, of course, if it gets an exception at 3, 3 is not the minimum. Let's try 2. Another exception. Let's try 1. 1 works. So current best option is 1. We try 0. Another error. So this means that the minimal scope for which it worked was 1. So in this case here, the find min scope, there is a test case for this for list, and it says for node it was 0. For list, the minimum scope was 1. Right? So that's exactly the things that you have to check, but you have to figure it out programmatically and not manually playing with the code. So again, there are some hints. So we are again restricting it to the first command in the Alloy file because you can imagine that this is specific to the command. Then to programmatically update the scope of a signature, there is this, if the command is called cmd, then you can call cmd.change. You give this signature which you want to update. You just leave this false, the second parameter, and then you give the new scope that you want to use. So that's the new kind of integer number, the ones that we were trying here. And so that's how you can programmatically update a command. This method here will return a new command which has the scope for this signature set to this number. And then you can analyze that as usual and check if it's satisfiable or not, and then decide whether you found the minimum scope or not. Now, you need to find here, we were looking at this and saw, yeah, let's take 3 as the maximum that it could be, but it's not always that simple. There are different ways that scopes could be defined. So for example, if nothing was written, then, well, here it turns out to be 3 again. But I think there are some cases, for example, if nothing is given here, then it's suddenly 4. So if no command is there at all. So that's why I already created a method that calculates the maximal scope for you by kind of guessing it. It's also in this Alloy checker. So this method here, get max scope, it tries it with 4, then checks if an overall scope is given. This was this kind of 3 that we set. So then that is taken. But if the scope is again refined for this particular signature, then we take the maximum scope of that overridden signature. So you simply can use this method to know for any signature what is the maximum scope that you need to try. And then you need to probably go down from there or do something more clever. But basically the output again should be a map that maps names of signatures to the minimum scope that you can put to still have a satisfiable run command or a satisfiable command. Okay. Yeah, and that's basically the stuff you need to know for task 3. Again, there are test cases for task 3. That's the min scope test. We already saw these. So Yeah, tasks 1 and 2, finding dead signatures, finding core signatures, and then task 3, computing the minimum scores to still be satisfiable.